All right, thanks for coming, everyone. I'm Tor Norbye, and I'm going to talk about static analysis with Android Lint. So this is a quick orientation of how the talk's going to go. I'm going to talk a little bit about Lint's philosophy, then cover some user-oriented features in Lint. Then we'll talk about how to write an actual lint check, and then some infrastructure features that Lint has for writing lint checks, some gotchas at the end, and then a little bit about the future. So what is Lint? Lint is a static analyzer, which means that it examines your code without running it and tries to find bugs in it. It was released in 2011, version 1.0, and it is free and fully open source under an Apache license. And at this point, it has about 315 checks. So there's two guiding philosophies for Lint. The first one is that false positives are better than false negatives. So ideally, we don't want false positives, don't get me wrong. But Lint tries to err on the side of caution. So it will surface potential bugs to the users, even if we're not entirely sure. And Lint has a bunch of features to help you suppress warnings, right? So if it's telling you something that you're sure is not a problem, you can suppress it with attributes in XML files, annotations, comments. There's an XML config file you can use. And this is also convenient in the IDE with Quickfixes. The second philosophy is for Lint to focus on Android-specific issues. And the reason for that is that Lint is integrated in the IDE. And so the IDEs typically will tell you things like, oh, you're assigning this variable to itself. That's not right. You don't want Lint to then also repeat that warning and get yelled at twice. But over time, we've sort of started migrating away from this. So initially, we have some annotation checks here that'll tell you things like, hey, this UI thread in Android shouldn't be combined with this worker thread method. We then added some pretty generic annotations. For example, call super, which means that if you override this method, you need to invoke super. Or int range, which means this integer needs to be between 5 and 10, for example. And so many users told us they really love these annotations, and they want to use them not just in their mobile code, but in their server-side code as well. But they can't because Android Lint only works from the Android Gradle plugin. So I'm happy to announce that as of this week, you can run Android Lint outside of Android. We have a new Gradle plugin that you can apply in your pure Kotlin projects. And so all the features that you have for the Android Gradle plugin with Lint, you now have outside of it as well. And that hopefully makes this talk a bit more interesting for those of you who aren't Android developers, but who came for the static analysis part. You can use Lint for that as well. Oh. All right, so let's cover some of Lint's features. First of all, it is multidisciplinary. And by that, I mean that many static analyzers are focused on bytecode or Java code or Kotlin code. Lint looks at everything, right? Even icons. So it can tell you, for example, your launcher icon should have a round shape. The reason for this is that in Android, often bugs occur from a mismatch between something in XML and something in code. So here's an example. We have this story title identifier in a layout that is basically referred to from Java code, and we want to check that the cast is compatible. If Lint was just looking at the AST, like an annotation processor, it wouldn't be able to catch this bug. Lint is also designed for tool integration, so it's not just a command line binary that we execute from the IDE and then parse the output. It is basically packaged within each integration. So Studio ships with one version of Lint, Gradle another. It's all built from the same code base, but they have different features. So initially, Lint was integrated with the Ant build system and Eclipse. Today, it runs in batch mode in the IDE. Each Lint rule pretends to be an IDE inspection. And it also runs on the fly in the editor. Around 75% of Lint's checks can run on the fly. And we'll see how to do that in a bit. We also have Quickfixes for Lint, and you can package those with your own custom checks. And Lint is also integrated in Gradle. So obviously, there's a Lint target you can run, and it can break your build if any errors are found. As of 3.1, this also works for Kotlin. So I know some of you were already sad to discover that in 3.0, you could run Kotlin checks in the IDE. Now it also works from the command line. And the Gradle integration also has this really detailed HTML report. So it does syntax-highlighted snippets showing you the error. And you can also drill into the explain button here, and you can see a fuller explanation of what the problem is, because often one-line summary doesn't really convey the subtlety that Lint is trying to convey to you. And if you like Darkula, like I do, here's this secret flag you can pass into the HTML report to get Darkula syntax highlighting snippets instead. All right, Lint also has a feature to solve the problem where you ship bugs into production because you forgot to run Lint. So the way we can do that is that in Android, we know the difference between a debug build meant for your computer and a release build meant for the Play Store. And so every time you build for the Play Store, we run Lint on a subset of checks. We call this target Lint Vital. We basically look for issues that have fatal severity, and we will enforce those. So there's around 40 checks today that are considered part of the fatal run. You can configure your own checks in your Lint options to say, actually, I want you to check for stop ship comments and break the build if anyone uses that in the code. Lint is also integrated with Jenkins continuous integration server, so you can look at your bug trends over time. And another feature that Lint has is baselines, which has nothing to do with the font concept of a baseline. The idea is that you tell Lint, record all my current options in this one file, my errors in this file. When you run Lint, it'll basically fail the build saying, OK, I created this baseline. It has 189 warnings in it. It's an XML file. You just check that into version control. And if you run Lint again, now Lint succeeds because there are no issues that it's never heard about before. And if someone on your team were to add a new warning, then the build will fail, but just listing that one warning. So this gives you a pretty quick way of starting using Lint without having to go back and fix all your problems right away. The last Lint feature I want to talk about is the support for custom checks, and I assume that's why you're all here today. You can write your own custom checks for Lint. Initially, there were teams inside of Google that wanted to do this, and so we came up with this pretty horrible solution where you just build your Lint rule and you drop it in this shared directory, and then Lint looks for it. Not great for reproducible builds. So we have a much better mechanism now, and that is the AAR packaging format. So when you, in a Gradle project, depend on an Android library, what you're really depending on is an AAR file, right? And AAR is really a zip file that contains code, but also resources, manifest, ProGuard rules, and Lint rules. So this is the Timber library's AAR file. So if you basically use the jar command, you can look inside, you can find Lint rules. I know someone on the back row wrote these Lint rules. And so when you have a dependency on a library, Lint will look at the Lint rules that came with that library and enforce them on the usage of your library. In 3.0, we have a better packaging mechanism for this. So basically, you have your Java or Kotlin project that defines the Lint rule, and then you can in your app project use the special Lint checks scope. And now Lint will apply that project as a Lint rule. And if it's a library project, it'll package it. All right, so that's hopefully enough motivation. Let's see how we can write our own Lint checks. But before I do that, I've been wanting to give this Lint talk for many years, but I always held back because Lint does not have a stable API. But what's happened is that lots of people want to do this anyway, and so despite Lint breaking API every release, people still do this. And so I thought, OK, let's give a talk and get the information out there, but I want to make sure everyone also hears this. Lint's API is not stable. It will change again. And at the end of this talk, I'll discuss what the remaining steps are before we can sort of support the APIs in a stable way. One more thing, I'd like to encourage all of you to write your Lint checks in Kotlin. And not just because it's a nice language, even though that is a good reason. About half of Lint's API classes are at this point written in Kotlin. And as we're making these changes, I'm using Kotlin's deprecation mechanism. And you can see it in this screenshot. There's this replace with parameter you can pass into deprecation, and the IDE will use that for quick fixes. So when we can make API changes that we can express in this way, you'll just have an Alt-Enter in IntelliJ to update your code. Not all the incompatible changes will be that easy to deal with, but that's an advantage. Another reason to use Kotlin is that Lint is going to make use of more and more extension methods. And so in your code completion, you'll find the extension methods. If you're writing it in Java, you have to discover these utility methods on your own. So what we do is we first create our custom Lint check project. It's called a custom check. It's the same terminology from Android's custom views. When you extend a view to have your own behavior, that's a custom view. Custom checks are your own Lint checks. So we basically apply the Lint API, jar as a dependency, and the testing support. And you have to know the special Lint version to use. And the magic formula is Gradle plugin version plus 23 for historical reasons. So Lint actually has two APIs. There's the client API, and there's the Detector API. And obviously, our focus here is the Detector API. The client API is the one for people running Lint, so the IDE, Gradle, and so on. There is one really important class or interface you should know about, though, from the client API, and that is the LintClient. Right? This is an interface implemented by the IDE, and it has several important methods. For example, there's the report method. This is where your detector says, I found an issue, please report this to the user. In the IDE, the LintClient implementation will probably put that in the editor with an underline, right? And in Gradle, it'll record it into a list so that it can spit out an HTML report at the end. Another important method is readFile or readBytes. No code anywhere in Lint and no code anywhere in your detectors should ever read files from disk. It should always go through this indirection. And the reason for that is that in the IDE, when anyone calls readFile, the IDE will say, is this file open in the editor? If so, what is the current contents of the editor? And it'll return that. So a file is just a handle referring to a file. It's not the actual contents. And that's what lets Lint run on the fly in the editor as you're typing. And we don't have to do something gross like save all files every time Lint runs, right? Another example from LintClient is open connection. If a Lint check wants to connect to the network, you call this method, and in the IDE, it'll use the IDE's proxy settings, the user's proxy settings, for example. And from a unit test, it's very easy also, right? You can basically tell the test Lint client to mock this, and whenever anyone asks for URL A, return contents B, and so forth. All right, so now we're ready to write our actual Lint check. And so the way we do that is we first create and register an issue that we return from an issue registry, and then we implement a detector, which reports the issue. And then, of course, we need a test. So what is an issue? Let's take a look at our HTML report again. An issue has a title, which should be a very short summary. It has an ID, and the ID needs to be unique. It's typically upper camel case, and it needs to be semi-user readable, because this will show up in users' suppression annotations. It'll also show up when users are configuring their Gradle options to increase or decrease the severity of the issue. We also have a category, which can include things like performance or correctness or security and so on. There's a severity. So we have warning, error, or fatal. And again, fatal is enforced error, right? That's the one that'll break the build if someone uses it. Priority you can ignore. And then there's the explanation. It's a little short here, but sometimes it has to be a lot of text, right? And so in the IDE, for example, when the user gets one of these warnings, notice that there's this little hyperlink at the end where you can get more information. If you press that keyboard shortcut, you get the full explanation that can convey more of the issue than the subtle one-line summary. When you write text to Lint in issues, in warning messages, you get to use a special text format that is a subset of Markdown. So you can use backticks for code symbols, and there's bold and italics and so forth, and you can also escape with a backslash if you need to. And finally, an issue registration can include a URL for more information. It can have multiple URLs. So here's how we write an issue. Issue registration, you don't subclass it. It's a factory method. You pass in all the data we've just discussed. And then you return that from an issue registry. So just subclass issue registry, return a list of issues. You can have many. And as of 3.0, you don't have to use this gross manifest key anymore. You can use the normal service loader mechanism, and Lint will find your issue registry. The other thing that I glossed over in the issue registration is the reference to our detector class. That's the code we are going to implement, right? So we basically list the class and the scopes that detector cares about. So a detector is basically the code that is going to be running on the user source code and is responsible for identifying patterns that are potential bugs. So we registered from the issue, and multiple issues can use the same detector. So for example, there's one detector which looks at all your dependencies and Gradle files. That one will report totally unrelated issues. Things like, hey, you're using dynamic dependencies, or there's a newer version available across the network. So here's the simplest detector there is. It basically runs on all manifest files. Manifest files because in our issue registration, that's the scope we reported. And it'll unconditionally report an error for this file with this message. No one does that, though. So Lint has a number of detector specializations. These are feature interfaces that makes it a lot easier to write checks. So for XML files, there's an XML scanner you can implement. This lets you visit the file with DOM. There's a UAST scanner. That's how we're going to do our Kotlin analysis. There's a class scanner that lets you use the ASM bytecode library to visit the bytecode. And there's a bunch of other ones for other file types. So let's take a look at the XML scanner. So this basically lets you tell Lint that you care about this set of tag names. And Lint will then call your visit element method for that tag. Similarly, there's a way to tell it which attributes you want to be called back for, or potentially you want all. So here's our detector again. Now we're saying that we don't ever want to see a tag name placeholder. If we do, we're going to report an error, not on the file, but on that specific element. So here's our unit test. Lint has a really rich DSL for writing unit tests. So we're basically describing here the test files we want to pass into Lint. So it's a manifest file. And then we're saying which issues we want it to run against it. Then we tell it to run, and then we expect a certain result. So notice how actually, let me go back. Notice how in the source file, we are including, OK, I'm pushing back. It's not, I guess I don't know how to use this. There we go. Notice how we're describing the source file in line in the unit test. I really like that because you can look at this test and you can see what it's doing. You don't have to go to some other file to look at it. But in the IDE, you have a much nicer experience than this green text. In the IDE, you get full nested syntax highlighting. This is one of those core features in IntelliJ where they do language embedding right. So this works not just for XML. Here's a Kotlin example. And notice how it's even running quick fixes on that sample Kotlin code, which is pretty handy. So let's look at our test again. We have a violation of our check right there in the unit test. And when I write a new test, I basically start saying, I expect to see nothing out of this test. That's not right. But what I can do now is run. There we go. I can run my test. It'll fail. I then see the failure message. I copy that in. And now we have our correct unit test, right? So we see the expected lint text output on the bottom from the source file that we passed in. And notice how I've inlined the full HTML report here. I'm sorry, text report. I've seen some custom checks do this instead, where you're saying, run the checks, and then I expect to see exactly one error. Or it might even say, I want to see this substring. That works, but there's actually real value in checking the full content to make sure nothing unexpected shows up, and more importantly, that you have the exact error range you expect. So here's our check again, and I've added some more report methods. Notice that for XML contexts, I can not just report an element. I can say, I want you to highlight the name portion of the element. Or for an attribute, I can say either the name portion or the value portion of the location. So if we run the lint, the unit test now, I have the wrong font. That's unfortunate. But anyway, you can see that for the two errors, one called getElement, one called name location, and we're only highlighting a smaller portion on the second one. And it's good for unit tests to check that you're highlighting exactly what you want. All right, we started talking about locations. Locations basically point to a file. For source files, unlike icons, you can also typically point to a range of text within location. There's convenience methods, both from the XML part and for the Kotlin part, to create these on the fly. And you can link many locations together. And you can describe those linked locations. So here's an example of that. This is a lint check, which looks for duplicate resources. So you don't want to say, hey, this is the second time I've seen this. You want to point to both occurrences, right? And that's how you do this in the code snippet below. You can make your second location and then add a linked list, basically. Point to the earlier location, link them together, and you can provide a user message for that linkage. So remember how I said that in Android, you typically have to look across multiple file types to find issues? So let's go back to that scenario. What we can do with our detector now is implement both the XML scanner and UAST scanner, which is the way we analyze Java and Kotlin. So we would basically look at both files and cross-reference it. But how do we store that data? Well, when we register a detector, we register the class, not an instance. So Lint basically guarantees that it'll instantiate a new version of your detector each time it runs. And that means that you can stash all your data on the detector instance. And furthermore, Lint has a predefined iteration order. It'll always follow this order. It'll always look at the manifest first, then resources, alphabetically by folder type, then Java, and so forth. So in our example, we don't have to we know that we're going to process the XML first. So when we get to Java, we don't have to store that 2 for the end. We can basically report the issue immediately. But what if we need to go back and look at the XML again after looking at the Java? Well, for that, Lint supports multipass analysis. So a lot of global analysis is easier if you can go over the data multiple times. So Lint lets you request another pass through the data, and you can keep doing this. I think it'll cap it off at like 5 passes. That's just to prevent really, misbehaving lint checks. So you can request another pass through the data, and now you can look at your earlier data and report new errors. So here's an example of this: the unused resource detector. In the first pass, it'll basically go through, record all the resource declarations and all the resource references, which may come in any order. At the end of the first pass, you can see, was there any resource declaration that was not referenced? If so, it'll then request another pass through the data, and you can look up from any lint check which current phase you're in. And if you're now in the second phase, now you know to report errors for any resource found in the unused resource map. So on the polar opposite of doing that, of passing through multiple times across all source files, is running checks on the fly. So essentially, Lint will run your check on the fly in the editor if your analysis is limited to a single file. And that's basically determined through scopes. So when you register the detector, you tell it which scopes this detector applies to. So here you can see 2 different issue registrations. The second one is the unused resource detector. You cannot determine that a resource is unused unless you look at everything, right? Because it could be referenced from just, say, the manifest. So the scopes for the unused resource detector says, I need to look at all these file types. This check will not run on the fly in the editor. But the first check, it's just looking at your XML files, looking for hard-coded text. It's a string reference. Those can be done on the fly, and so Lint will run this on the fly in the editor. And there's an expert mode you can use if you want to report some, but not all. And there's also unit tests for doing these incremental checks. They're called incremental. It's not a great name because it's not what you think it is. This is basically an unfortunate name from the days when Lint was running in Eclipse, and what this was doing was incrementally updating the problems view. But you can think of this as the on-the-fly feature. So XML Scanner was an easy way to visit XML files. To analyze Kotlin code, you should be using the UAST scanner. So what is UAST? Lint has gone through several APIs for describing the Java syntax tree over the years. And as of 3.0, it is using something called UAST, which is a universal abstract syntax tree. The core proposition is that it describes a superset of both Java and Kotlin. So when you write a lint check, you don't really care or know whether you're dealing with Java or Kotlin. You see logical things like class declaration, method call, if statement. And so your lint rule will basically work on both. And currently, UAST is implemented for Kotlin and Java, but it could be implemented for other languages. And if it is, then your lint rule will work on those as well. So in UAST, everything is a U element. But there are sub-interfaces for other things like compilation unit, class, method, and so on. And as you'll see, the real focus of UAST is the stuff inside methods. So here's a source file that I've implemented twice, both in Java and Kotlin. It's a very simple one. It's a class with a string field. And the tree is on the right. You can see that we have a compilation unit. Then we have a class with a field, and then identifier and literal expression. So as you're learning UAST, you may wonder, how do I identify a switch statement in Java, right? And here's a really useful tip. What you can do to explore UAST is to write a unit test. You see one here for Kotlin. And in your handler, call this one method as recursive log string. This will dump out the hierarchy from UAST, which I've included below on the slide. So you can see not just the structure of the tree, but you can see the name of the interfaces that your visitors will need to be looking at. One really powerful part of UAST is that it can resolve references, including to things outside your source file. So let's say I have a call into a label variable that's pointing to a setText method. If I call resolve, this will basically point me to the method that this is calling. And I get that back, and I can now look at the containing class, I can look at the parameter list, and I can even look inside that method. And several lint rules do just that. But notice that resolved actually returns a PSI element. So what's a PSI element? PSI is the older interface used in IntelliJ to model source files, and it's still in use. UAST is not replacing PSI, it is augmenting it. So a U class is a PSI class, a U method is a PSI method, and so on. But the converse is not true. A PSI method does not have to be a U method, and typically it's not. So you'll resolve a call into a library. That method in that library is just known as bytecode. It is not represented by UAST. So you'll need to be able to handle the PSI stuff. So basically, PSI is what you use outside the method bodies, and UAST is what you use inside. When you resolve, you're going to end up with a PSI interface. And so it's extremely important that when you get a PSI method back, you don't call getBody on it to go inside the method. Because in your Java unit test, that'll work just fine. But in Kotlin, getBody will return null. You need to call these UAST methods instead to basically get the UAST representation of the method body. So armed with the syntax tree, you can do a lot of analysis, but it's actually a lot of cumbersome work. And also think of the performance implication. If every lint check were to do their own full walk of the AST, and there's over 300 lint checks, that means that we would visit the tree 300 times for every source file in the project. So that's not what you do. So we have the UAST scanner, which is this feature interface similar to XML scanner, which helps you write lint checks for Kotlin. So there's a bunch of callbacks. So for example, you can say, I want you to call me whenever a method of one of these method names is provided. So for example, call me when someone calls a method called makeToast. Or when someone instantiates a given class, like I want to know when someone instantiates a fragment. You can look for symbol references. So your lint check may say, call me whenever someone references a field called serial version. Or subclasses or subinterfaces. So you can be called back whenever anyone implements parseable. You can check any Android reference like r.string.foo. That's how the unused resource detector works. You can also visit annotation usages. I'll talk about that in a little bit. Or you can visit any AST nodes by type. So here's an example. We want to look at the code sample at the top. So we want to find calls to this method on alarm manager, set repeating, and we want to check the second parameter to make sure it's something small. That's what the purpose of this one lint check is. The way we do this with UAST is we say, OK, we care about method names called set repeating. Whenever lint encounters that method, it's going to invoke our visit method. And what we do there is we make sure that this method is actually the one on alarm manager. And there's a convenience method for that. And this is how lint works quickly, is it builds up this lookup table up front, right, from all the methods to the corresponding interested detectors. And then it could do a single iteration through the code base, just dispatching to the right detectors. So back to our detector. Now we found our method call. We know that it's to the right class. Now we want to make sure that the second parameter is less than 5,000. How do we do that? We call the constant evaluator. So this basically will figure out, given a parameter, it'll walk its way backward, do some flow analysis to figure out that this value is 200 and return that to us. So that's a really handy utility. Lint has a bunch of these important helpers that it's important to know about. So there's the Java evaluator. This one helps you make decisions about inheritance, for example. It's actually a poorly named class. Obviously, it's dealing with Kotlin, not just Java. And it's really just a utility class. So this will probably be moved into extension methods soon. And there's a bunch of utilities that you should know about. The constant evaluator is the one we just saw. But one difference between this constant evaluator and the one that compilers often use is that our constant evaluator is willing to consider non-constant things. So you can say, I'm willing for you to look at field values even if they're just the initial value. And this goes back to the earlier philosophy that false positives are better than false negatives, right? Sometimes it might not be correct, this might not be constant, but you can find some real bugs this way. So here's an example. Here's a lint check that wants to look at SQL strings. And it wants to make sure that you are using the text type, not the string type, which is a common mistake. In some cases, it can't figure out the full SQL query, but we can tell the constant evaluator that we are happy with getting portions of it. And in that case, we get it back, and we can do our check. Lint has a type evaluator. So for example, here, even though view is of type activity, Lint can figure out that it's really a list activity, and that's really handy in some checks. Similarly, we have a resource evaluator. Poor slide conversion. Basically, it figures out what the corresponding resource is being passed into a method. There's a lint utilities class. This has an edit distance method, among other things. This makes it really easy to figure out whether there's a simple typo, right? If there's a small permutation to a string you can make to bring it to something else. There are a bunch of other utility methods. I'm not going to cover them all. It's just important to know these exist because they'll make writing your lint checks a lot easier. And I'm not going to cover all the UAST scanner callbacks either. I'm just going to cover annotation support because it's brand new in 3.1. And this basically makes it very easy to write checks that deal with annotations. So you specify the annotations you care about, and then Lint will call back all the places that seem to be relevant to that annotation. For example, if you annotate a method, it'll check each exit point from the method and also all calls into that method, and so on. So here's an example. I want to write a lint check for the check result annotation. That if you annotate the method with check result, it means that we expect callers to look at the return value. So here we're telling Lint that we care about that annotation plus a bunch of aliases that mean very similar things from other libraries. And then we just override the visit annotation usage method. It gets invoked. Here it's going to be on a call. We look out from the call and see is anyone assigning something or dereferencing this result. And then if not, then we report our bug. Kotlin introduces, again, the weird arrows with the slide conversion. Kotlin introduces a complication to mapping between arguments to a method and the actual parameters, right? Because of things like name parameters, default parameters, var args, extension methods. And so there's a pretty useful argument mapping utility method in the evaluator you can call, which basically you pass it each argument to a method, and it'll return a map, actually, that has the mapping between the parameters and the arguments. And for the annotation check, this is handled automatically. So if you're being invoked on a parameter context, it's going to be linked correctly for you. Let's talk about quick fixes. So you can also package quick fixes with your custom checks. It's a pretty limited facility, I have to warn you. What you're providing is basically a descriptor of how the IDE should address the problem, and then there's an actual implementation on the IDE that executes that description. So here's an example. We have a lint fix for a check, which is suggesting that you replace some calls with some other calls. So we basically name our quick fix, and we do a string replacement, and then we pass it into the report method, and then the rest just works. And there's really good unit testing support for this, right? So after our normal expect method, where we're checking the output of lint, we can then also tell it to check the fix diffs. What this means is it'll take your sample code, it'll iteratively apply each quick fix you registered, take the output of that, diff it with the input, and append it. And that's how we see here that these various quick fixes have been applied, and you can see what they did. Quick fixes, you can be named. You can actually make a composite quick fix. You combine multiple together, and they'll all be executed as a single quick fix. Or you can have a group, which means the user in the IDE will see alternatives, different ways to fix it. For XML, you can call set or unset to manipulate XML attributes. But the most important, the most powerful way to deal with this is the string replacements, right? So you can say, I want you to replace all the text that I highlighted as an error, or some subtext, or a regular expression match within that text, and replace it with this other string. And you can use back references from your regular expression if you want in the replacement text. Here's an example of a lint fix. So we want to add a cast in front of find view by ID. So what we're replacing it with is a fully qualified name. Users don't want that in their source code. So 2 lines above that, we're calling the shorten names utility method. That tells Lint, actually, after making this, I want you to then apply a shortening where it's going to import the class instead and replace all the symbols in the replaced fragment. Similarly, the reformat suggestion means that it's going to insert a space after the parenthesis if that's what the user's code style is configured to do. So even though we can analyze the UAST source tree and not care whether you're talking about Java or Kotlin, that is not true for manipulating the source code, right? So we had hope at some point that there will be a convenience API that would let you do this. In Studio 3.1, we're working on closing the gap between our Java quick fixes and the ones available for Kotlin. So we might come up with some convenience layer that could help with this. But for now, you need to handle each language separately. So in the case of the cast, that's not how you cast in Kotlin, right? So you would look at the source language and provide 2 different fixes based on what you were doing. Android also has support for, Android has merge manifests, right? Where the results are coming from different sources. In Lint, you typically had to add your own little code that looked at each manifest and did this merge for yourself. You don't have to do this anymore. You can tell Lint, I want the merge manifest. This works in the IDE as well. And you can report errors, and it automatically maps things back to the source code. So this makes it a lot easier to do sort of whole program analysis without having to do the manifest merging on your own. And this is maybe the most exciting slide for me, but it's not very detailed. We are working on a new call graph, right, that lets you do interprocedural analysis in Lint. This is in 3.1. We will tweak the API for this a lot. It's very expensive to compute. But we have one Lint checks that's using this today. It's an interprocedural thread analyzer. It figures out long call chains from one thread, one API annotated with one threading annotation to another one, and the intermediate call chain does not have to be annotated. This is going to let us write Lint checks that are much deeper. We're going to have fewer false positives, and you can basically use this to do whole program analysis. We will be tweaking this heavily in the future, but I'm really excited about this, and I want your feedback on it. I've also mentioned a couple times that Lint has a really rich test DSL, so definitely explore it. It's going to be worth your while, I think. Right, let's talk about some gotchas. These are some things to look out for when you're writing your Lint checks. So you should make sure you have at least one Kotlin test for your Lint check. Right? So Lint has over 300 checks. It has really good code coverage, but a lot of those were for Java source files. And I discovered that there are a lot of things that you need to special case for Kotlin. So for example, if you ever do PSI method.body, or worse, or more commonly actually, you do an instance of check. That may not work correctly in Kotlin. So you'll be operating in PSI space, and things are operating in Java PSI space, and that works for Java, but it fails for Kotlin. So make sure that you have at least one test that is actually exercising your Lint check from Kotlin. When you are looking for return values, don't do what some of our Lint checks did, which is to visit all the uReturn expressions, right? Because in Kotlin, you may not have a return expression. There are expression body methods, and UAST is not inserting a fake uReturn there. So you need to be able to handle this correctly. So make sure you have a test for this if you care about exit points from a method. Variables may not have type declarations, right? So in this code sample, the variable is going to have a null type reference. That doesn't mean you can't get the type. It's there in UAST. You ask the expression for its type, but just look out for that. There is a binary operator that sometimes you'll be using, for arithmetic. For equals, just be aware that there's equals and identity equals. Our code was missing this. So for Kotlin, there's a double equals and a triple equals, and you want to make sure you handle both. Let's talk about Lint 2.0, finally. So I've already said that the version of Lint is 26. So by Lint 2.0, I really just mean the next generation. That's going to be the stable supported one. So UAST was the first thing on our list, and that is now done. But we want a much more powerful Quickfix API. We need an improved registration API. The primary purpose of this is to let Lint run a lot more efficiently in the IDE, where it's running over and over every few keystrokes. Resource repository lookup. So this is most relevant to you who are writing Lint checks for Android. But in order to do Lint checks on the fly, you can use the resource repository to look up, for example, all the locations of r.string.foo and actually find out what the declaration is. This works today, but it's only available in the IDE. And so when you write a Lint check, you have to sort of handle both cases, and that's not great. So it's going to be a mandatory part of the LintClient API. KTS support. We have some support for Gradle files. It's not great. Gradle, of course, is going to support Kotlin files very soon, build.gradle.kts. So we want to make sure that, that we are handling Kotlin script natively in Lint. And a lot of people have requested an options API for Lint rules. So you may want to say, hey, I want to take a string, an integer parameter, or as a range or something like that. So we want to have some way for your Lint check to declare this, and then for it to automatically work, that users can configure your Lint check from build.gradle, and also to build a little UI in the inspections UI so that people can customize your Lint check without having to set environment variables or system properties or anything like that. I already mentioned the call graph support. That's going to be some more work, but I think we want to have that API so that Lint can really do whole program analysis efficiently. And then there's the stable API, and there's a bunch of work involved with that. We're going to rip out all the old code that we no longer want to support. We're going to rename all the places that are currently called Java. I just didn't want to rename them UAST yet because it's just going to unnecessarily break things. But when we make that big day, when we switch over to incompatible API, it's going to all be cleaned up and it'll be UAST everywhere. And then a lot of these utility classes that I pointed to really should be extension functions, so that from Kotlin, you can just explore things with code completion and find it. You shouldn't have to know that it's SDK utils, SDK common, and so forth. We have a community. So, I actually had a lot more slides, if you can believe that. This was 140 slides. I had 180. If it wasn't entirely clear, which I suspect it wasn't, please come to this community and ask your questions there. It's also an open source project, so if you want to write lint checks, not just for your company, please contribute them and let everyone get the benefit of your static analysis. And with that, I am done. Thank you very much.